Multisoft Virtual Academy, with over 21 years of experience, offers 1,500 plus courses, partners with 10K plus experts, serves 2,000 plus corporates, has trained 1 million plus individuals, and earning a 4.5-star rating. Here we share the overview, benefits, and facts.
Now on the OrcaFlex background, so now as you already mentioned, you've already used OrcaFlex, so you may have seen some of these features and capabilities. So it's of course, a world-leading software package right now. So in the last 10 years, we have seen that the usage of OrcaFlex has increased in oil and gas industry. So typical applications are in the form of basically we run offshore dynamics, including marine renewables, riser systems, which could be SCR, TTRs, flexibles, etc. Mooring system, mooring analysis can be done, all different types. Then installation analysis. So we have full range of scenarios. There are some non-standard scenarios as well, towed systems, then seabed stability, and many other types of system which can be done. So you can see in the photo as well. We have a floating wind turbine analysis which can be done in OrcaFlex, which then we have a suction anchor installation analysis here, a jacket installation. Then we have a FPS, so turret mode FPS, mooring analysis with some risers connected to it, lazy wave. Then we have some fish farms also. Like OrcaFlex can be used for these. There are some tools, workspace tools which is not generally used. I mean, you can play with the thread count. You can see the speed index of your machine from here and change the preference of like how the window is. Then workspace is just to create a particular arrangement of different windows in OrcaFlex. And window is like we can have different an additional window here. Like if I click on this 3D view, so it should create a new window. So you can this way, and then you can tile it in different ways, etc. This is more like visualization, but most of the things which happens in OrcaFlex happens in these three, like calculation, model, and results. And we have the same repetition of all the different objects. So this you may be already aware that we call each of these different component as objects in OrcaFlex. So we have a vessel object, line, 6D buoy, 3D buoy, winch, link, shape, then wind turbine, constraint, etc. So these are all objects. So you can either access it through model or you can directly click on them and you can access it. So just by clicking on that and then clicking on the window, it will generate a copy of that object. Then we have the same buttons which are under results here. You can run a static analysis, you can run a dynamic analysis, you can pause a simulation, you can reset a simulation, and then some replay parameters and a replay bar. So this once you run the dynamics,
Yes, please. Can you shed more light on these replay parameters, because I want to understand it or later you explain more, or you just go around this. Okay.
Yeah. So let me see if I can open a simulation file, because this replay will only become active to be used when we have a dynamic simulation, a completed dynamic simulation. So once the simulation is completed, so we have modeled the all the objects. This is a lifting analysis or a lowering analysis, in fact, where we are lowering some small object, conical objects here. And once the analysis is completed, we have run the dynamics and the simulation completes. So it will be in the complete stage. So at that time, we can use this 4 button to see how the dynamics motion. We can see the motion of the object. So if I press this start replay, so it will start from the time t equal to 0, and it will move all the way till the end time of the simulation. So you can see the replay time here. So it started with -5 seconds and it will go till end. We can control the duration, the time duration, using this bar. So we can move this. So if we move it back, we can this will, and then we can also stop the replay. So with the first green button, so this was green initially, it started the replay, and we can stop the replay. So it will again come back to the final dynamic complete state. Also use this yellow button to have a step replay, or we can also give a time here. So if I give a 10-second here, 10, so it will stop at 10 seconds. So you can see replay time. So now if I go to this yellow, the arrow beside this yellow, so there's a drop down.
Yes.
I hope it is
Okay. Yeah.
visible now.
Okay. Yeah. It's
Yeah,
showing now. Yes.
yeah.
Good.
So here I can give the duration at which I want to reach in the replay. So if I press
Okay.
10, then it will reach the 10-second.
Right.
And I can also press this yellow button to have a step replay. So right now it is 10, and if I press, it will go by one time step ahead. So it went to
Okay.
10.1. If I click, so
Mm.
it will, you can click and it will move, but these are step replays. So it will not be a continuous replay, but the number of times you press this, it will move those many time steps ahead.
Right. I
Yeah.
get it. Yes.
Yeah. And then
Okay.
we can also set some replay parameters. So
Mm-hmm.
we can see the replay for the whole simulation. So here we can select each individual stage for the replay, or we can include the whole simulation, or we can just run the latest wave. So for regular wave, we can run the last wave of the simulation. When we are running the analysis, we can have two types of waves. One is regular wave and other is irregular wave. So what happens is, a regular
Every.
wave is the same wave which is repeating,
Yes.
right? An irregular wave is more of a spectrum. It is generated through a spectrum, and it doesn't have a repetitive pattern, but it has the same property of the spectrum. So right now, if you see in this particular simulation, we have a Dean stream, and Dean stream is a regular wave. It's a type
Mm.
of a regular. This is a regular wave, and irregular wave could be anything, like it can go up and down. So it's, but
Mm.
the properties, the energy of this is equal to a spectrum. So that we can discuss a bit more later as well. But
Right.
so this latest wave only comes for a regular wave system, where you have the same wave which is repeating. So what we can,
Mm.
and generally if you run a riser dynamic analysis or a mooring analysis, what we do is, there will generally, once we apply a environment, there is a transition period where the system will start uh, acting because of the forces, and then it will attain a steady state. So after some duration, so for example, if we are looking for a tension response, and when we
Mm.
start uh, applying a wave, so it could be, initially it could be a little random response, but then after some time it will become steady. So as the waves
Mm.
are coming, it will move with the wave. So what we generally do is, because we want to see the exact effect of this wave, we we can take just the latest wave as well, because we know that after a
Okay.
duration, once steady state is attained, we can just take the last wave and find the response of that, right?
Mm.
Yeah.
I
So
get it.
yeah, so OrcaFlex
Mm.
give this feature of plotting
Latest wave.
a result for a latest wave, and same thing you can run a replay also for. So if I just take latest wave, it will only run for the latest last wave, how it is behaving.
Okay.
And
Okay.
in fact, there are some guidance from the standards as well. Like if you have, we have to run the simulation for at least 5 waves, so that 5 to 10 waves, so that we are able to attain that steady state. Otherwise, if you only
Mm.
run one wave, there is a chance that
Wave seed. Yeah.
so yeah, so I think this is the latest wave option. Then
Mm.
specified period is, we can give a uh, s- uh, the length start and the finish of the replay. So instead, so if you don't, if we give tilde here, it will start from the ramping stage all the way till the
Mm.
last stage. But we
Mm.
can give maybe starting from 10 seconds to maybe 15 seconds. So what it,
Mm.
and if I press OK, so it will only run in between that. So it will run from 10, it will go to 15, then come back to 10. So here,
Okay.
so you can control the
Nice.
range of the replay from here. Speed,
Mm.
you can control using this bar or using the value cell here. So if I
Okay.
increase the speed, it will, this replay speed will become that much of percentage of the actual simulation.
Speed. Okay. I
Because
get.
for mooring analysis or riser analysis, a standard is to run the simulation for 3 hours to account for the full sea state. But we cannot view the, we may not have that much time to view the full 3 hours at the real time speed. So for that, we
Mm.
can make it faster, and we can view a longer duration in the lesser time. Then this is just a same add 3D view button, which was also available in the window. So this will generate a new view, new window to view the model. You can also we have some more parameters on the left side of this view. So you can there is a graphic view where we will be able to see the solid 3D objects, and then we have a line frame view. So you can uh, change it using this shaded graphic mode button. So if I change it, it will come back to the original line frame view. Then we can use this magnifying button or the screen moving buttons as well, rotating buttons. But generally what I have observed is people rarely use this. They will use the mouse and the shift and control buttons to move. So if you press control, it will rotate, and if you press shift, it will move translationally like this. Yeah. So but you can control those using these buttons. And if you want to zoom in, you can press control and use the cursor, mouse cursor. So if I move the cursor up, then it will zoom. If I move the cursor towards me, it will zoom out. Right.
Okay.
Then we have the results tab. So results tab is used to see all the results. So OrcaFlex has a very nice help feature where in fact, if you see any issue in any of the location in OrcaFlex when you're using a form, you can just click on that cell and press F1. So it will take to that exact location where that particular cell is explained. So this is useful if we are using any new form in OrcaFlex. So if I use maybe vessel type and I want to understand what this value reference origin is, so I'll click on this cell and I'll just press F1. So it will take me to that exact location. So I've felt that this is a very useful feature in OrcaFlex to when we are. Then on the left side, this window is called as model browser. This could be accessed through the model tab as well. So if I press on this, it will disappear. If I want to bring it, I can bring it back. And here we can see the complete list of all the objects and the data points in our model. So that could be accessed from this window. So it's divided into two parts. First is some data which is shared data, which is used in different files, and then we have different objects. Objects here, which are the actual components in our model. So we can also group similar types of components, or we can ungroup them. So if I unselect this view by groups, we'll see that all the similar components are grouped together in OrcaFlex. But I felt that view by groups is a useful feature where you can have different subcomponents and keep them together and name them together. So I felt this is a useful feature. So if you have two different lifting happening, so you can have first one as in one folder and then second one in a different folder. So it's easier to keep track of very large complex models. And if you press F3, I think you should be able to just see that particular. So if I click on that folder and press F3, I'll be able to see the it will blink. Yeah, same for yeah. And this is the vessel.
Okay.
Then in terms of the shared data, again, I think I'm sure you must have used these data, but maybe let me start with one of them, which is this general tab. So so it starts with we can assign the units of the model. So how we want to. So if you change it to, you will have three options here. Let me go back to the demo model. So you can have SI units. So it will take meter, tons, kilonewtons, seconds, etc. You can select US units. So it will change it to feet, or you can also have user-defined units. So here there will be a drop down where you can select. So one of the good feature in OrcaFlex is if you already have a model available and you have selected then I think most the other useful tabs in this is I think analysis is one of them. So here on the right side, I think you already mentioned about the stage numbering earlier when we were discussing on the simulation. So you can have OrcaFlex always have one ramping stage, and then we have different. So as it's similar to when we were discussing that when a wave is applied, or an environment is applied on a system. So sometimes what happens is OrcaFlex is a numerical software. So so sometimes if you have a system and then you apply a very high load on that,
Right.
so there is a chance that it may become numerically unstable. So what OrcaFlex does is it will ramp all the loads in the first stage. So by ramping, it means that at when the simulation dynamic simulation starts, all the loads will be zero. Like if we have a current ramped, it will apply a zero current. Although we know that we want to check for a current of maybe 10 meter per second. What OrcaFlex does is at the start of the simulation, it will assume it to be zero and then gradually ramp it to the full current. So that happens in this stage one. So similarly for wave as well. So if we define a wave of maybe if I give a wave of here, it is 20 feet. So it's not like OrcaFlex will apply that wave instantly, because
Right.
there is a risk that if you apply all the loads instantly,
There's a what? There's a risk.
There is a risk for the model to become unstable.
Okay, there's a risk for them. Okay, I see what you mean. Okay.
Yeah, because if you apply a very high impulsive load to a system, then the convergence may see some issues. So you can also control the ramping of the current using there's one of the tab here called ramped, which we'll discuss again when we come back to the environmental tab. But you can also switch off the ramping. So there may be cases that you want the current to be applied completely from the instant the dynamic simulation starts. So we can uncheck this. So if we check this, the current will be ramped, and if we uncheck this, it will not be ramped. Then on the left side, we have the static, enabled, and dynamic. So here we can control if you want to run statics and dynamics both, or if you uncheck dynamics, then it will only run statics and it will stop there. And if you have both of them checked, it will run dynamics. Let me check what if you have both of them selected. OrcaFlex will first run the statics, then it will run the dynamics. If you don't have dynamics enabled, it will stop at statics, irrespective of if you use any of the button. But if you just use dynamics, OrcaFlex will use the reset stage like as the initial configuration. But I won't suggest that to be a good option, because when you create a model, or generally in a reset stage, it may not be an equilibrium state. So for example, here you can see the line may not be in an equilibrium based on wind and current. So general practice is to first run statics, and then we have some other parameters which we can use to control the ramping time as well. Yeah. So here we are giving the stage durations, and here we can change the exact time when the duration is starting. So if I give a higher value here, so it will start from 10 seconds. So before that, it won't have any simulation, and it will start from 10 seconds, and it will go. So at 10 seconds, our ramping will start, and we will have the second stage after that. So this is more like playing with when this particular durations will be. Again, this is not very useful. Most of the time, people will keep it as standard, as tilde. Then we have some statics parameters and dynamics parameters. So in static parameters, first, so we have two types of buoys. So for 60-degree of buoys, here there's an option to control the degree of freedom in statics. So as we saw that when OrcaFlex starts the simulation, it will first run the static simulation, then it runs the dynamics. So we can control on what all degree of freedom it should solve. So if we give all here in degree of freedom in statics, it will solve all the degree of freedom. So it will also consider it free to rotate. It will also consider it free to move. But if I give XYZ, it will assume that in fact it will behave like a 3D buoy, because we have fixed all the rotation. But as soon as the statics get completed, when the dynamic starts, it will assume it to be able to freely rotate. So
really,
yeah. Okay. So if we give XYZ here, in statics it will be fixed rotation, but in dynamics it will allow it to rotate. So this is available for all the 6 degree of buoys, and we can control it individually. But in case if you want to control for the whole model, then we can come here and then select. So if I select none here, all the buoys in the model will become none. And if I select XYZ, all of them will become XYZ. And if I give, there are some cases where, for example, towing of a towing analysis. So towing effectively, so if is a, so when we are towing a structure, so what we see is it will have some, basically your vessel is moving from in the water, and there are some, we can give a speed here in the, so basically this will assume that the whole system is moving with a steady state velocity in some direction. So all the static forces will be applied based on a motion, so you'll have some inertia. So this will discuss a bit more.
Okay,
this we can for now,
yes, please.
once we start modeling. And most of the time this is not used because we generally run dynamics and all the motions are being considered there. So this we almost 90% of the time this will be 0. But maybe I'll give you some examples where we can have this as some value later. Yeah. Then we have line static policies. So you can see there is a step 1 policy and step 2 policy. So in OrcaFlex, everything happens in steps. So we have already discussed on static step and dynamic step. The static also happens in 2 steps, step 1 and step 2. So maybe let me do one thing. I'll just first go through what exactly are those steps, and then we can come back, because here it's more like including all the lines or not including them in step 1 and step 2. So basically step 1 is, do you want to include all the lines or do you want to not include all the lines in step 1? So if you don't include it, it will skip the step 1, whatever you are giving in here.
Yes.
Yeah. And same for step 2. So this is just
control,
like control of what is being included. And now if I go back to the different algorithms in step 1. So maybe I'll start with the easiest one, which is analytic catenary. What does this mean is, so these mooring or risers. So basically this is only applicable for line object. So this you may be aware, right? You may have used line objects in OrcaFlex.
Yeah, I've used line.
Yeah. So when we are running a simulation, it has to start from some initial shape, right? So OrcaFlex has to take some initial shape, and then it will use that and slowly start converging to a equilibrium shape. So basically what is happening in statics, OrcaFlex is trying to find an arrangement where it will attain an equilibrium. So all the loads like gravity, your buoyancy, etc., will bring all the objects in equilibrium and it will not move. So that is called as static equilibrium, where all the loads become equal to each other and effectively there is 0 force on the system, and the system has become reached a equilibrium state. But to reach that state, it has to start with some initial shape, right? So for example, maybe this is the equilibrium shape in OrcaFlex. Once the current has been applied, maybe we are applying a current from the right side, and the line will move on the right and it will stop there, right? If we apply a current from the left side here, right? So, but OrcaFlex has to know that where should it start from, so that it will know from what parameter we are giving here. So if I give an analytical catenary, so it will use some analytical equation. So there are some empirical equation for a catenary line. I'm not sure if you have heard about those. Like a catenary will have a shape. So all these chains, etc., will take this shape. So it will assume that shape as an initial point, which you can see here, and then start the equilibrium from there. And so you have one is analytic catenary and one is catenary. So so there, if you want to create a line with some curve, maybe a curve, and there are some spline lines in that. So what it does is you can give some marker points around the line. So for example, this is one line, and then this is more like a curved line. So there will be some marker points like this.
Right.
And if I move this marker away, the line will start moving with it. So this is called a spline line. So what we do is we give this marker points in OrcaFlex. There are some 4 control points here. In fact, if I select this, you will be able to see those points. So if I move them, it will move those. So it's exactly like how we do in AutoCAD. And when we run the simulation, this will be the shape that the line will take as a starting point instead of the analysis catenary. Yeah. So maybe if we already know that, okay, line is going to be getting pushed by the current in this direction, so we can give a spline. So this may be useful sometimes when we have lines on the seabed, and we may want to give a profile of the line, so we can use a spline. So for example, here I can just give a profile like that, in this way. So it's not vertically going down, it is going at an angle, it is in the horizontal plane as well, it is moving. So this we can give a different starting shape than a analysis catenary. So analytical catenary will always be vertically down, because there are only 2 forces in the statics. One is your gravity and weight. So it will always take this shape, vertically down. But if we want to give a profile on the seabed or on some shape, etc., then we can use the spline to give a shape to them. So it will start the simulation from this and then try to attain an equilibrium. So this will be the initial shape of the line. And similarly, there are 2 more ways to start the initial shape. One is called prescribed and other is user specified. So in prescribed, instead of giving control points, we can actually give the actual points of the lines. So here we are giving we are giving that the point which is at length of 164 should be at XYZ value. So instead of so the difference between spline and prescribed is, in spline we give only few points which are control points, which are visible here. You can see they are outside the line. In fact, like you can see this is outside the line. But if I go back to prescribed,
where are the remaining 2 points for the spline? There are 4.
The remaining 2 points are the ends.
Okay.
Ends of the line. So if you see here, you won't be able to even change them, because those are just taken from the end, fixed end A and fixed end B. So they are copied, and all the middle ones you can change. And so it all depends on the segmentation. So if I make a 100-meter line, so for spline it is still 2 control points. And if I go back to prescribed, here also I'm giving 2 values. So what it does is it will take those 2 points and it will make a line through it. You can see this line here. So here, so it will fix the end at these points, the second end at this point, and then it will use these points to lay the line. Like the length at 300 will be at this position, the length at 100 will be at this position, and the remaining line it will form in between based on these points available.
Sorry, I didn't get that.
So what it has done is we gave a fixed value for end B. So it took that as the point. So you can see here, this is the point where it is fixed. Then the remaining points are used to control. So the 300 here, you can see this line, right? So it's fixed at 86, but now if I change this to 200, you will see this point has moved here now slightly. And if I change 67, so this point has come to 67. But if I start increasing it, instead of 67, I make it as 80. So it's moving with that. Yeah. So you can play with this, but mainly it is like we are giving the exact points on the line, and it fixes based on. So another thing is this is useful. So if I have 0, so what has happened, because I only have 2 segments, so all the bending in OrcaFlex happens at the nodes. So what do you mean by that? So when we are defining a line is made up of multiple nodes in OrcaFlex. So and the nodes are same as the segments. So this is a segment, and each node will have between each segments there will be a node here. And you can see the line, the one segment behaves like a rigid rod in OrcaFlex, and all the bending happens at the nodes. So you can see here. So because I only have two segments, so what it has done is it is trying to bend here. But if you see, both the segments are straight. And if I start increasing, maybe I'll reduce the segment length to maybe 150. So still there are only two segments here. If I reduce it further to 100, so now we have three segments. So it is now bending at these points. So our number of segments should be high enough, or our target segment should be low enough such that it takes a proper curve in OrcaFlex. Otherwise, if you give very high segment, then it's more like you are just having three rigid rods and you are. So then we were giving spline and prescribed. There was a tab which was opening, and there were a limited number of entries through which we can control. We can increase those control points or these points on the line. But when we do user specified, it will be equal to the number of segments. So like if I have 164 segments, you'll have 164. So what we are doing is, in this we are giving value for each of the point now, all the points on the line, all the nodes.
Okay,
So
yeah, getting the coordinates of all the points.
Yes, yeah. So it will take, so if I have maybe 100 as the length and only 3 nodes, so we'll give all the 3 node values. Like basically 3 segmentation is like we have 2 points which are moving and 2 points fixed. But if I start increasing to 30, so it will have more points. So the difference between prescribed and user specified is, in prescribed we only control few of the points at some lengths. But for user specified, this length part is not even there. So in user specified, we are controlling all the points. We are giving values for all the points. There is another difference between prescribed and user specified. I mean, the way we use it. So once we have run the simulation, so for example, these simulations are completed. So sometimes what happens is we may want to, when we run a simulation in OrcaFlex, it starts from an initial shape, which we can give based on one of these options. And this may not be an equilibrium state, right? This could be some initial shape. It could be a cat. So what happens is, when we start the simulation, OrcaFlex will try to, so how this calculation is done in OrcaFlex, it will try to find an error from the equilibrium state to the initial state what we have. So initially it is like this, then it will start moving to a equilibrium shape, and then once it sees that the error is low, then it will stop there. So there will be some time it will take to run the simulation, right?
Yes.
Yeah. So there may be cases where you may want to run the same statics multiple times, like you are changing some parameters somewhere else here, maybe on the vessel, but your line is still the same. But every time when you run the statics, you are starting from a non-equilibrium state. It takes its own time to run the equilibrium. So there is a way to tell OrcaFlex to start from the equilibrium shape itself. And how do we do that? We run the simulation first. First time we have to run it, it will start from a which is connected to some pile here. So and the statics is complete. So you can see here right now, when we started the simulation, we had given catenary. So catenary is we have given, it will take based on the end position. Like this is the end position, this is the other end position. Based on that, it will calculate some values. But once we run the simulation, what may happen is your vessel may move, your end positions may move, and it will attain the equilibrium. Now I don't want to, next time when maybe I want to update something on the pile. So I'll stop the simulation, then vessel will go back to that new position again, or older position, again in the equilibrium state, then again it will come back to this position. To avoid that, what I can do is, when the statics is complete, I'll go to model objects. I'll use this option of use specified starting shape for lines. So what it does is, there is one static line orientation. So there are 3 different initial position update we can give. So I think we discuss on this user specified starting shape, which is only for applicable for lines. We can also give line orientation. So if you see here, there is I think you already had touched upon this end connection, azimuth and declination, right?
Yes.
So this also, so if we have a pin connection, so you can see maybe I gave this as the initial orientation, but in reality the equilibrium orientation may be the other side, right here, like this. So what happens is, after the equilibrium is attained, it will actually have the equilibrium orientation, and we can set that using this use static line end orientation. What it will do is it will then set the values, set these values as declination gamma based on the
Okay.
equilibrium values.
Okay, I see. What it's similar to the for values of the line, but this is now for end connections.
Yeah.
It will change the orientation.
Exactly. Okay. Yeah. So we can test this also maybe once we are running some models, but and same thing is for calculated position. So what this does is, so now my initial vessel was at this position, and when the equilibrium started, it came here. All the system. So if I use so what it is doing is in the step 1, it wasn't considering the bending stiffness. Right, in analytical category, in fact other cases also. So step 2 is if you keep it as none, then it will take whatever shape is achieved in step 1. So if it is a user specified, it will just use that as the initial shape when it is starting to run the dynamics also. But if I give full statics, so what it does is in statics all the objects are fixed, our buoy are fixed, our vessels are fixed, but line would try to attain the equilibrium position. So maybe so line is here. So what we did was in the first step we gave some initial shape. So this is step 1 is basically giving an initial shape, and step 2 is static equilibrium.
Okay, I see what you mean. It's like a step. It first solves the lines in step 1, then it now solves the static equilibrium of the whole system.
Yeah.
In step 2, okay, full static.
So step 1 is not there's no algorithm happening here. It's just this is one of the starting shape it will take. So if I give user specified, it will take the user specified shape from this. If I give so here the difference is in static and dynamics there is no wave acting.
Yes.
And they will move, but there won't be any time history to it. So no, but yeah, you're right. I think I stand correct now. So the buoys and vessel will move. Even the line objects it is connected to, it will also move, and this will only happen in step 2 when step 2 is happening. Step 1 is basically you're giving some initial shape.
Supposition,
yeah, and step 2 is when all the objects will move and rotate as well. But there won't be any wave or any time history to it. It will be like just
agree.
take a
it's just statics.
yeah, correct.
Okay.
Thanks for pointing that out. Yeah,
thank you.
Yeah, okay. So I think going back to the general tab again, so we have again here we can control for the whole system, like do we want to have none, only the all the lines included, or parent line included. So parent line is like you can connect a line to a line. So if you are connecting one line to a line, so the line which has been connected, so we have step 1, then we have step 2. In fact, maybe this is the same thing what we were discussing a little while back on the objects are not moving, right? So whole system statics and then dynamics. Right. So these are, you can think of the equilibrium attaining in 4 stages. So what happens in stage 1? Stage 1 is we are just giving the type of initial shape for the line. So we can give it as line, we can give it as a catenary, or so there's no simulation getting solved here. So it's just the initial shape we are giving prescribed. In stage 2, what happens? So there is a difference between stage 2 and whole system. So in stage 2, this is the stage which I was referring. Actually, stage 2, all the buoy and vessel are fixed. So again, coming back to that. So this is, in fact, I'll just mark it also. So this is the statics part. This whole is statics. So statics is happening in 3 stages. So first is step 1. Step 1 is just initial shape we are assigning it. Step 2. So in fact, all this progress, when you run a simulation, you may be able to see in the status bar. So this is the status bar one. I don't have a license, otherwise I would have shown. Like once you press this button, initially it will show line statics.
Yeah, I know the status bar. I have OrcaFlex now, the license one on my system.
Yeah.
I can show you when we start to do modeling.
Yeah. So, but this is good to know, because you will know when exactly. So if your step 2 is failing, we'll know that okay, the issue is in the line. If the whole system statics is failing, we know the issue is in the whole system itself,
yeah,
not just the line. So that way you'll be able to do, and
you'll
then
be able to troubleshoot. That's what you mean.
Yeah.
Yeah.
And,
okay.
Yeah. So that is what comes here now. So there is a checkbox for whole system statics enabled. So if I uncheck it, it will only set the lines into equilibrium. All our shapes, objects like buoys and vessel will take the initial values of position what we have given here. So it won't move from here. Like if you don't select this whole system statics.
Clear. Nice.
Yeah. And then we have some convergence parameters. So we have convergence parameters. So because we are now running 2 different stages, right? So our equilibrium, coming back to this, is happening. So just one question before we go. Where exactly is the equilibrium solved now? Like we already discussed, I just want to throw one question. Is it stage 1, stage 2, whole system statics? Where is which all stages is static equilibrium getting solved now?
It started solved in the whole simulation.
Yeah, whole simulation. But whole simulation is for all the 3.
Right? Yes.
Yeah, but we also have static simulation getting solved for line in stage 2 also. So only line is there, right?
Yeah.
Yeah. So it's basically.
Was it only line you asked me, or the whole system?
Sorry.
You said where is static simulation solved? I was saying, is it for whole or stage? Because stage 2 is for the line only without the buoy and the vessel.
Right. So static simulation for line is happening in stage 2.
Yeah.
And then whole system, which is like including the line, buoy, etc., everything together, then happens in whole system. So we have a static equilibrium only for line here, and then for all the other system here. So it happens stage 2 and for particular object, and stage 3 for all objects. So yeah. So that's where we have these parameters. So we need convergence parameters for stage 2 only line and then whole system statics. So these are the parameters OrcaFlex will use to attain the equilibrium. So whole system statics parameters are present here on this form in general tab below the line, and line statics parameters are for each line given in the line itself. So you'll see there's a tab for static convergence. So it looks very similar, both of them. So we have number of iterations, what is the tolerance, damping. So number of iteration is like OrcaFlex will go in iterations. Like it will first check the error, then it will move the line to a new position, then again check the error. It has reduced or not. If it has reduced, it will go towards the same direction. If it is increasing, it will go to the other direction, so that the error is reduced. So what OrcaFlex does is, first it will go to step 1. Step 1 is just the initial shape. Then step 2, it will see here how many iteration it has to take. So it will start it. It will run for 400 iteration. If the error is less than 1 e power minus 6 before 400, it will stop. So it will go and keep on checking the tolerance. Tolerance is basically what is the error from the equilibrium. So it will keep on checking. If the error is less than 1 e power 6, which is maybe at 100 step. So this is the initial stage, initial values what we are given, and maybe this is the final equilibrium stage. So this is equilibrium. We know that it has to come here, and this is the initial, like we gave some prescribed shape maybe in this case. So this is the initial value. So now when we start the simulation, so this is stage 1 now. Stage 1 is completed and it has reached here, right?
Yes.
Now in stage 2, it is now starting. It will come here. It will check what is the tolerance. So now what it is observing is we have the line which is not attaining the equilibrium. So maybe tolerance at this point is 10, and it is less than the tolerance required. So it will move it at some direct distance. So this distance, how much it has to move, is controlled by the damping. So if I give very low damping, it will move by a larger distance. So maybe, so for example, let me just draw that. So this is maybe our equilibrium position, and assume this is the shape we have given initially. So this is the same line, just we are saying that this is the equilibrium position, and this is a prescribed shape we gave, which is very different from the equilibrium position.
Yes.
So now once we start the simulation in stage 1, it has reached in this prescribed shape. Till this, I hope it is okay.
Yes, it's okay now. I can see the size.
Yeah. So now OrcaFlex come to this parameters, and now it is checking what is the tolerance value, required tolerance value. So we have given 1 EPA 1 is 6, and then it will calculate the error in this. So for this, because it's very different from the equilibrium shape, maybe the error is 1000 here. It's a
right
order much higher than the value. So it has to now try to attain an equilibrium, right? So now what it does is it will take these values, and based on this it will calculate a delta value. So delta is how much it should move towards the equilibrium side.
Yes.
So delta is inversely proportional to the damping. So these damping values. So these both of them work together. So we should give these numbers slowly. But if I give a very low value here, 1 in 100, 1 in 10. So what will happen? Delta will be very high. So this delta will be the new position where it reaches. So this will maybe a new position in the first iteration. So it moved here. So this is the delta 1. And then it will check what is the error. So error is maybe 100 here because it is more closer. But if I give very high damping, maybe 100,000, so what it will calculate the delta, and delta will be a lower number because we are giving high damping and it's inversely proportional. So it will maybe just reach a slight, there will be slight variation from the initial shape with this delta. So this delta is very small. So here error is still 900 because we have only gone from 1000 to 900 here error, but here it is 100. So what happens is if you give very high damping, it will slowly try to reach to equilibrium. But if I give very low damping, it will take larger steps.
Okay, I get it now. Yeah.
But what happens is if I give very low damping, sometimes what happens, now I came here to 100. So next step will be maybe 10. Maybe next step could be the other side. So it may miss the equilibrium also. So now in this step, this was the step two right now. So we solved only the line right now using the full statics of the line. Now we are going to whole system. So whole system parameters will control from this general tab. So same thing happening. Now instead of just the line, we also have the vessel. So here, so again, as we discussed, no lines are included. But couple system, it's saying couple group of lines. So if there are two lines which are grouped together, they will be getting solved. Yeah. So this coupling is between the lines.
Okay, no, we don't. When I look at system, I'm looking at the whole. Okay,
yeah, I think the nomenclature is confusing here, but this it means just the line.
Yeah. Okay, so this couple system means the line, the parent, and the children. That's what it looks like. If you see,
that is right. Yeah.
Okay, great, clear. Thank you.
So you may have like in the starting phase of OrcaFlex initially, like around 6 to 7 years back, we didn't have the option to connect a line to a line. So this only came, I think, 5 years back, if I'm not wrong.